STL Iterators. This relates to assignment 1, obviously. Hands up who's started assignment 1 now. Okay, a lot of people. That's good. Did anyone take my advice and just try and commit like crap to assignment 1 just to get going? You did? Yeah. Congrats. I love that. That's good. I always like to know my limits. All right, so a fairly kind of short and brief lecture on this, I guess, in a way, because there's not an exceptional amount to talk to. And we covered it a little bit before. Iterators are abstract notions of pointers. Like references, they are not pointers, literally. Well, I mean, they're very different to references, but they're both a reference and an iterator are similar in the sense that they are abstractions of the idea of a pointer. But they do things very differently, because a reference is literally going to be a memory address to that pointer. Whereas an iterator is going to, again, be an object of a class that contains some stuff. It just happens that you can treat that object itself as if it is a pointer, when in reality it isn't. So iterators are types that abstract that. Iterators will allow us to connect, blah, blah. And we talked a little bit about this, but just to rehash it, most STL containers will have 2 member functions or methods, depending on what you want to call it, called .begin and .end, that follow this particular pattern. We did that little bit with memory last time. But what's interesting is that the iterators themselves, and the iterators are what's returned by a.begin. So an iterator object is like an object, Java, Python, whatever. It's a class. Someone goes and defines a class called vector iterator somewhere. And when you do vector.begin, you get that vector iterator object. It's not really an object you think much in a concrete sense, but it exists. And what's cool about it is that you can treat it like a pointer because these two operations are valid on it. So you can do a dereference of the iterator object, and what you will get is the value the iterator points to, and you can do a ++ on the iterator object as well, and it will feel like a pointer to some memory address. And we can play around with that here if we want to. We've got an example called vector iterator. We're going to go pull that up. So here's a piece of code. Again, I do apologize. Some of the lecture code is older and doesn't have the always use auto styles in it. I'll probably get a tutor to come and clean that up. And what I mean by that is that we kind of say, based on the best practices guide, that this is not a good line of code, and it should instead be auto names equals standard vector, standard string, like that. That would be the right way to write that. Some of you might write it like this. The difference between those two we'll talk about next week, but for all intents and purposes, they're the same for now. So we create ourselves a vector of strings. It's totally empty in this case, and then we would iterate through it and do something. But let's add a few things to this vector. A, B, C, U, just to throw people off, D, E. So we've got 5 letters in it. 6 letters, can't even count. So we're going to iterate through it like that. And we've already seen this, so I'm not going to go into a great deal of depth, but we can dereference it. And I can also show you again, really quick, just to rehash it, that if I can probably just start with that. And I'll comment out these 3 lines. We'll quickly make the program, which we probably just to the build folder, sorry. So I'm going to go make vector iterator. Can we dim the lights? Yeah, we can dim the lights. Hell yeah. How low? You got a choice between 50%, 25%, or 0. 25%? Hands up for 25%. I don't remember. Hands up for 50%? Hands up for 0%? All right. Democracy. Get rid of these 2. I find these ones quite intimidating. I hope I'm still visible. Ugh, that'll do. All right, so we already got some errors here. Oh my God, it's a C++ error. Oh crap. That's a big error, isn't it? Lord. So the interpretation of this error, these errors will start to make more and more sense to you throughout the term. invalid operands to binary expression, basic O stream, and iterator. Oh, no. What's going on here? Any ideas? Bracket it? That's a good idea. I like that. I don't think that was it, but I like that way of thinking because it says binary operation, so it's like bracket the pointer. You mean this one? I think that one's okay because that was. I mean, if you think about it from kind of first principles, if I get rid of this, it should build. So it's the addition of that line there, right? But you're right about like putting brackets around things because order of operations, like we're not all geniuses and remember the exact total breakdown all the time. Probably should turn that back on. It's quite bright. I'll bring you down to 0. There we go. You're all happy. What's happening here is that it is basically complaining and saying that C++ does not know how to turn that particular type into a string. Because what happens is when you are trying to output stream it, it has to essentially turn it into a string. Now, if I try this, that worked. And this is something that's like really weird and interesting, because let me just try and run this program first and we can talk about it. I probably have to put a space there. So here's the funny thing about, oh yeah, hot tip, most of you would know this, but if you just ampersand your program and then do that, you can just build and run it the same step. Save you 4 seconds of your life. I've got all my numbers there, and then I've got the memory address of iter, which in this case looks like it's not actually iterating. Ah, that's because it's the address of the iterator objects. This is where things get really weird. Because you have to imagine that this is the only tool I remember every time. You have to imagine that, you know, in C, obviously memory is going to be a whole bunch of blocks, right? We know this, and we know that if you have a little pointer, and a pointer here itself might be, you know, 8 bytes. This is your pointer. That pointer will point to a particular memory address. It's just how C works. Every pointer in C on a 64-bit machine is 8 bytes. Doesn't matter if it's a char star, a vector star, anything. It's always 8 bytes because it's just a pointer to memory. However, when we go and create an iterator object, we're creating, oh my God, I'm sorry. We're creating something quite like fat and chunky, right? Do you remember creating classes in your other courses? And those classes have private member fields and stuff. So just for, you know, to scale, your vector object, your vector iterator object might be like this. So when you do your vector.begin, it high fidelity content, hell yeah. Cool. This is your like vector iterator object. So you call your vector.begin, right? You get your vector iterator object. It's an actual object in memory, no different to the vector itself. And what that means is that when I'm trying to print out iter like this, it's complaining in this case because it is saying that it doesn't know how to print it. Right? It can't print the object itself. That just means whoever defined the vector iterator object never defined a way for it to be printed. Or more specifically, and we talk about this in week 4, they never defined a way for it to be streamed to an output, which is the fancy way of saying there's no like toString method on it. However, you'll notice that when I did the ampersand on it, where things get funny here is that all those memory addresses are the same because I'm actually printing out the address of the vector iterator object itself in memory. Because this big object here is probably going to have a subcomponent of it, like this, and inside of that is itself going to be a pointer to a particular element in vector. I love paint. Let me just round that box for you. Yep, cool. So you got your vector iterator object, and inside of that's going to be some actual more basic type. And what this thing is here is this actually points to that at the start. And when you increment the vector iterator object, it starts to point to here. So the vector iterator is just in a chunk of memory, but it contains something that is kind of keeping track of where it goes. And that's, in that way, it's how it's an abstraction. And that's how when you do things here, like dereference it, you're actually going through an abstraction where there would be a function that's being called for the vector iterator class type that would say, hey, my job is to dereference the underlying pointer here, you know? And I don't know how it's implemented because I didn't design it, but that abstraction again is what can help us provide more safety. So for instance, someone could reasonably create the vector iterator object to know what the start and the end point is, and if someone tries to dereference something that isn't between those two bounds, it could, for instance, throw an exception or something like that. I'm not saying that's what it does, but that's the power of these abstractions for us. So there you go. I can still print out every element, but my main point here is this is not a pointer. This iter is not a pointer to the element you're trying to display. It is an object. And when you dereference it, it's kind of passing through that object, and the object is itself going and getting it. It's a proxy. I've probably said this like 7 times now, and it's getting old. So really simple loop there. And then we've got another loop here. All this other loop here is doing is showing you the explicit type. It's the exact same thing. All it's saying here is that when you do auto iter equals names.begin, what it's actually going and doing, auto is becoming this particular type here. Because there is a class called iterator, like somewhere in a file, there is a class called iterator, and it just so happens that that class is wrapped up inside another class that will, what is it, template? We'll talk about more like what this syntax would be later on. So just so you understand it, there will be a class out there called vector, and inside that class, amidst all the normal class definition stuff, someone will have created another class inside of that called iterator. Yeah. It's like a whole range of emotions. I got a lot of head nods, and then I got a bunch of like faster sleeps. That's like my favorite thing about lecturing is you all don't see it, but like up here, I'm often talking to just like usually 3 or 4 people who are completely gone. For those people who sleep in lectures, I'm not upset. I mainly worry about your well-being. I would just go home, personally. Be comfortable when you sleep is my view. All right, so that's the example. We're just talking about those types. I'm mainly just trying to unpack the concept of this. The coding's not that hard. It behaves pretty intuitively. Any questions about this so far?
So it's not really a pointer here, but it's probably using it backend.
What I would say is that an iterator is not a pointer, but it's a class that contains the pointer you're thinking it is. And therefore, because it's just the pointer wrapped in a class, it's just the abstraction of the pointer. Someone asked on the chat, can you do iter less than .end instead of iter not equals to .end? That's a good question. So someone there is saying that, hey, I've noticed here that you say not equal to .end. Now, if you're a comp sci student, this should probably scare you a little bit, because what do you know about iterating through contiguous items? You shouldn't do a less than equal to, right? Like at some point in your degree, you've probably come across a scenario where it's been a bad idea, because what happens if something goes wrong and you like skip over the end condition, and then your program like loops forever. So it's pretty natural and intuitive to want that to be a less than. Feels a little safer, because if you kind of skip past it, then it's all good. The tricky thing is, and I think this is the case, this diagram that we have here, it's generally a conceptual diagram. It doesn't describe memory literally. If you're not sure what I mean by that, it's hard to picture that for a vector, because we know vectors are stored contiguously in memory. So it makes sense to say, well, there's the end of the vector. We deterministically could figure out that memory address without the iterator. However, think about that example we did with the map class, right? Remember, the map was an ordered associative container, big annoying words, and we said it was stored as a tree. A few people at the end of the lecture last week pointed out, I think it's stored as a red-black tree, which I actually don't remember how they work. Mild confession, when I got told to teach 2521 3 years ago, I was talking to a course admin, and I was like, do we really need to teach this? Because I don't understand it. And they were like, no. I was like, out of the course it goes. So I never actually had to learn it, that particular term. I have vague memories of it from my younger years. But that's what it's stored at. I think a few people confirmed that for me last week. But my point is, with this, when you get an iterator to it, what happens, particularly for a balanced tree like this, is that it will linearize this list for you. So let's imagine a quick bit of code. I'm sorry, I hate writing code that I don't compile because I think it's useful when students see that. But let's imagine that I have a main function, whatever. And then I've got my auto map equals standard map of say just a set, really simple set of numbers of int, easy. It's got nothing in it, and then let's say I go and I don't know, is it set? Do I remember the function? Do I have to look it up?
Isn't it in place?
In place? Yeah, sure. So someone went and in placed all these numbers, right? 17, blah, blah, blah. They go and do that with everything. And then they say, well, you know what? I really want to iterate through these. So now they go and create a loop. And they say, well, for auto iterator equals map.begin. Iterator does not equal to map.end. And iterator plus plus or plus plus iterator doesn't really make sense. There's my loop. And then I go and maybe standard C out the value. Now, if I did that, what I would get is I would get 1, 6, 8, 11, 13, 15, 17, 22, 25, 27, all in order. I'm 99% sure off the top of my head. I would get the nice linearization of a balanced ordered tree. Balanced is different, sorry. Like an ordered tree where all the numbers come up in order. And the dot end would refer to one past the end of the tree. But when it comes to a tree, how do you know what the end of that tree is in memory? Right? What if it's stored as a linked list? What if it's like whatever it is, like if I asked you to point to that diagram and be like, that's the end of the tree, you wouldn't really know where it is. And even if you did know, it's probably just a guess because that would be implementation specific as well. So the dot end, whilst we can conceptualize it as one past the end, it's not something that we could naturally maybe rely on because it's more just the idea that it's past the end. So we just use that to say we've gone too far, right? So we're using your kind of previous conceptual understanding. So the reason we don't say less than is because, back to this example, it wouldn't even make sense sometimes at all. Because these two things, like what's often happening here is not strictly a memory comparison. In fact, I don't know. I remember someone said to me years ago that like names.n could just be null if someone really wanted it to be. Like nothing would be particularly bad or wrong with that. Someone said, if so, is there any way to print the address of each item in the vector? That's a good question. We tried to do that before, right? And we got the compile error. Yeah, remember that from like 10 minutes ago? So anyone have any ideas? And I have an idea, but I'm sure someone else is following me. How would you print the memory address of the item? Because we tried to do it, and you know what happened? We got in trouble. Big trouble. 1,000-line trouble. So how would I figure out the address of each of those items? What would you cast it? You want to cast it. What would you cast it to?
Is it a bracket or a star?
You want to cast iter? So the problem with, okay, someone just tell me, maybe. You want to cast it to something. You want to cast iter to something?
Yes. I don't really know what you would cast it to make it.
The tricky thing is it is the iterator object. The pointer to iter gives, well, the address of iter, is that what you mean?
Yeah.
That gave us what we had before where we got the same bloody spaces. Put a big pipe there. That would give us what we did before. We got the same address every time because as we iterated through it, this kind of whole object that was the vector iterator is always the same thing. It's just it contains a pointer and that pointer is shifting.
Is there a method
Is there a method
exactly
that we can read it? That's an excellent question. I don't know. Let's go figure that out. Maybe. Standard vector, we can look for the begin and end. That'll tell us, if we go into that, it'll say it's of type iterator. Oh, I don't know where that's defined. Iterator. Oh, this is where the docs start to really mess with my head. I don't know, it's somewhere. I don't remember how to look that up. There's a member function called, oh, it's called data. Yeah, great. Genius. Beautiful job. So someone has pointed out to me that you can do that. Is it data? Sorry, now you're really stressed, I'm sure. But is it that one? Is it dot value? I remember something like this, though. So I know you're on the right track, even if we've got the... But there's something like that, because it's just a class, right? So you can just access it, yeah? Data. Oh, like that? With the brackets or not the brackets? I think we'd probably need the brackets. No. Well, that just gets us the same thing. Ooh, so confusing. OK, so someone in the chat, Tim, good job. You could, exactly, and you're on the right track as Tim on the live chat, which is, and here's the funny thing, right? If in C, you were to go and say, int a equals 5, and then say int the pointer b is equal to where a is, sure, you could naturally, what would you say? Like, so b is now a pointer. That gives you the value at b. And if you put the ampersand out the front of it, you kind of get the same thing, right? Like the address of the dereference cancels each other out. And in that sense, that's the same thing. So b is the same as dereferencing it and getting the address of it. But where things get weird with this iterator object is that I should be able to do this. I'll go and actually put that on the other side here. So there's my memory addresses. And why this is weird, and I like this example, and good thinking, Tim, is like, and someone on the anonymous chat's mentioned it too. Thank you, anonymous person. Welcome. Hello. Did you get some dinner? That's so smart. I always love that. There's like going to be 10 people here right now who are like, damn it. OK, so the reason I like this example is because normally you would expect, if that works, you would expect that to give you the same result. But it doesn't, and you've got to think about what's actually happening here. It's because when vector iterator is what it is. It's the object. So when you dereference it, you kind of say to vector iterator, hey, can you give me the value of whatever you're pointing to right now? And it looks inside itself. It looks at the pointer. Maybe that pointer right now is up here. And it says, yep, I can give you that value. That value might be 2. So it says, yeah, here's this value at this memory address. And then when you put the ampersand in front of it, what you're actually putting it in front of now is this particular memory address. Like you've kind of already gone to the iterator and said, can you give me that thing over here you're pointing to? And that's what you're dealing with now. So you kind of, when you get the address of that, you're no longer dealing with it. Now, that is not a programming problem you're going to have to deal with. But we're trying to understand what is going on behind the scenes here. Just make sure I haven't missed anything. Yeah, if it was a pointer, you'd be able to, address the dereferenced variable and the variable, and they should be the exact same thing. But it's because there's that object kind of proxy in the meantime. OK, with Iterators 2, we have a few extra methods. These aren't going to be super hard to explain. But we have constant begin and constant end, and we have reverse begin and reverse end, and we have constant reverse begin and constant reverse end. Just on the reverse ones to start. So the reverse ones are also fairly intuitive. If you do rbegin, you get the last element, and rend is one before the first element conceptually. Again, depends on the particular implementation as to what it is literally. But it's not like, and why this is important is that vec.begin does not equal vec.rend. If that makes sense. Because they're not the same thing. So don't get in your head that like, yeah, the the reverse end is the same as the normal start. They're not really used interchangeably like that, just because of how they have to end kind of outside of the object. And then we have our const begins, const ends as well. When you make something a const begin or a const end, you end up making it, it becomes of type const iterator. You don't have to declare that type because auto deals with it for you, but it is still here regardless. In the best practices guide on the course website, we talk about const correctness. We haven't really discussed that too much, except in week 1 we were like, anything that can be const should be const. If you don't need to modify it, make it const and keep it to be const. Where this then starts to come up in iterator land is that, similar with iterators, you should be using const iterators wherever you can as a signal that these things don't need to be changed. So if you're using any kind of iterating through things, then just make sure it's C begin and C end if you don't need to change it. And naturally, the other benefit of that is that if you try and compile code that actually modifies it in some way, you'll get a compile error. Someone, Sulux has said in the chat on YouTube, so this is back to the previous one. So the dereference isn't an actual dereference, it's kind of an overload on the star symbol. Yeah, that's accurate. And again, we unpacked that a lot more in week 4. Cool. Any questions about that? That one should be pretty doable. Someone says, if you use const iterators, can you still do ++ iterator? Hey, and someone also kind of sort of mentioned that. Yeah, you can. That's another funny concept. So what you'll notice is that const iterator, there's a difference. Like if you've got this type, standard vector int or whatever, it doesn't matter. Standard vector of int iterator. There's a difference between that being const and a const iterator, right? Because this one's a const version of a type. This one is just another type. It just has the word const in the name. It's just a different name. And that const iterator name simply says that this iterator object is obviously managing this kind of pointer to a container. And all it's saying is this object will not allow you to use it as a proxy to modify anything. So the question was like, can you still use ++ on a const iterator? And the answer is yes, we're doing that exact thing right here. I mean, we could print this out, right? We could use this particular const iterator to see what's inside our vector of 3 items. And I should be able to compile that fine. Const reverse. Make constness reverse. Perfect. Should work. Yep, so it works. And we can increment that because it's not like saying we can't modify the vector iterator object. It's simply saying that, like, you get what I mean, right? It's because it's the same thing. There's an object in memory like this, and it has a pointer inside it like this. And when you call increment on it, you are then asking it to go and increment the internal pointer. You can modify the vector object. You're just not allowed to use it to grab something and then modify that. Some interesting questions that come from this. I just got reminded of a question that I guess I got asked a while ago, which is like, well, if you think about it for a second, you know that the vector stores ints. So let's just say, what happens if we go and get, or like an automatic reference, and we'll say like temp equals iter, right? So we're going to go get a reference to the object each loop, and then I'm going to try and increment it there. Does that make sense? So I'm trying to see if I can like bypass that const element, because I know that it won't let me Like, what was the original example? I know it won't let me like dereference it, then increment it. So let's see what happens here. Who thinks they know what will happen here?
Is that setting it to the dereferenced value?
Yes. But it's a reference to it. So like you have to, like a reference has to be to a type. Like even though references are pointers, you don't have like you don't say a reference is this pointer. You say it's like the actual value. So I'll just see what happens here. I don't know. So 18, 19, and 20. I'm just messing around now, seeing what we can learn.
Set it as a constant order.
Did we set it as a constant order? Yeah, so this is where things get kind of interesting, because you can see here that when we dereference this, because again, we unpacked this in week 4. Honestly, like, makes me want to bring week 4 forward if I ever taught this course again. But imagine for a second, where was that? Let's think about how this is implemented. We have a class called Iterator. Somewhere in there is a function called like operator star. And what that function does is that will return what the value is pointing to. And just to keep this example going along longer, you might have something like this. This is how an iterator works in a nutshell. So you have a class that's an iterator. When you do .begin, so maybe you have a function here called like begin, and all it does is like returns a new iterator with something in it. Because maybe the overall vector has like a a C-style array in it. I'm randomly making this. Maybe it's got an array with 10 items in it. Something random. It returns an iterator that points to the first element. Again, just making stuff up here. There is a way you can redefine what that star operator does naturally, and by saying well, it's going to return type, maybe an int in this case. People following me with this? Nerve-wracking. But here's the funny thing. How this actually works is that somewhere out there's another class called Const Iterator. Someone will go and copy and paste this and change the name. So there's going to be 2 classes now, 2 different types of iterators, one for const and one for not const. And what they do is they say, well, when someone does iterator star, let's actually say that we want them to, that function has to return a const int. Does that make sense? So like for the implementation of a const iterator, when someone goes to dereference the value, the return type of that dereference action is a const type. It's kind of hard-coded into the definition. And what that means is that when someone like me comes over here and starts saying, ooh, you know what, I'll just like go and get that value over here, nice and safe. Even if you were to break it up even more and be like, well, int a equals iter, and then be like, yep, the temp reference, well, actually that would probably work. It's a different thing because you're not modifying the variable. But yeah, in this case, you can't really bypass it because this type here, right there, is an int const. Because that's what the dereferencing of the iterator object returns, is an int const. How's it going?
This would be a simple, like, kind of dumb question, but so how, under the hood, how's int and const different?
How is int and const different?
As in, is there like an if statement somewhere stopping it, or is that actually like there's a type?
Stopping the modification of it.
And everything, yeah.
Oh, that's like deep in the compiler. So like think about the compiler. So the compiler here sees it a star. It is a vector const iterator. So it says, okay, vector const iterator. Someone tried to dereference you. So it goes and talks to vector const iterator. And it says, hey, someone tried to dereference you. Do you have any way of dealing with this? And then it says, yeah, I got a way of dealing with this right here. Here's the function. The compiler's like, cool, okay, there's a function. What do you give me? Oh, you give me an integer const. Okay, cool. Well, now I know that it's an integer const. And then someone over here creates an auto reference. So it says, well, the right-hand side is an integer const. So the left-hand side is going to be a reference to a const integer 2. And then when someone tries to increment temp, which is a reference, the compiler's like, okay, wait, you're trying to increment a reference to a const integer. You can't do that because it's a const integer. So compile error, essentially. Yeah. It's like brain training, isn't it? All right, what do we got? There's no more questions there. People having fun on the chat. Great. You got no enthusiasm for pointers anymore, do you? Okay, not much more. Stream iterators. I don't think these are particularly exciting, so I'm not really going to talk about them, but because you don't really do them in the course. But for streams, like input file stream and output file stream and all that kind of stuff, you might have come across an input file stream for assignment 1, trying to read from the lexicon. You can also use iterators on it, though it's not really something that I would spend too much time thinking about. We're just kind of saying that they exist. One thing that I don't think's in the slides that should be is there's this concept of iterator invalidation. So the key word there being invalidation. And invalidation is when the iterator you have, you should no longer use. And it's kind of referenced a little bit. If you kind of look at vector, there's a function in vector like erase. So you know vector.erase. And you'll notice that for the erase function to work, it always wants an iterator. So you can't pass in an index or anything. It's probably, again, just a nice way to abstract it. Because if you're passing in an index, I don't know why it doesn't like it. But it needs an iterator to work. If you're not too sure what I mean by that, let me try and write a quick bit of code for you. I'll just go and delete all this stuff here. So I was just reading the chat. Horrible coughs. All right, so this is how I write code. I'm a dummy, so I write that first, and I get that compiling before anything else. And I say, all right, well, I can compile code. Easy. 2.2 constness reverse. All right, so I can write code that compiles. That's good. Now we'll go make ourselves a vector. Auto-vec equals standard vector. We'll make it of strings, because strings are fun. And again, we'll do ABC. And now let's say I want to delete B. Well, to delete B, if I want to use the erase thing, one way I could do that is I could say auto iterator equals vector. I believe there's a dot find in it. There's not a dot find. Ooh. That's good. Well, it's not good, but maybe I'll use that to kind of springboard into the next one. But really simply, I could say vector.begin. And let's say I want to get rid of the second element. I could just say, you know, iter ++ or something like that. So iterator is like incremented by 1. So I've gone from the first element to the second element. And then I could say vector.erase that iterator. Does that make sense? And then what I'll do is I'll print out the array, the vector again. So I'll say like auto const. Sorry? I don't know. I just assume there wasn't. Yeah, I don't think there is. C++ is mean. Item in the vector, standard cout. Item. A and C, we deleted it. OK. Great job. Aren't I smart? You know, pinnacle of my capabilities right there. So let's have a look at erase again. What I want to point out with erase is you look for this word invalidated. Iterators and references to the elements at or after the point of the erase are invalidated. What that is saying is that any iterators you have at that value or past it, once you call an erase function, you can no longer trust those iterators anymore. C has a lot of stuff like this where, you know, C and C++, these ideas of like undefined behavior, where it says you can do some stuff if you want to, but like we're taking no liability anymore. You know, like hands off, it's your fault. If you want to see this in action again, we're just exploring these things as we go, so some of these examples might not go well. Let's imagine before we erase it, let's actually imagine we go and create a second iterator. This one I'll call iterator 2. And this one will also be vector.begin. And this time, though, I'll increment it by 2. Right? So this references B. this reference is C, now this reference is B at this point, and then I do vector.erase here. And obviously this code should still work, mostly. Use of under, yeah, but let's see what happens when I try and standard C out iter2. What will this give me? Interesting question. Sorry? C. I did get C. Did I? Got nothing. Horrifying. This is because, like, if you think about it as a programmer, imagine you're a vector iterator. You're just pointing to some spot or some value, and when someone goes and moves stuff, that variable moves. So imagine that. Imagine the red-black tree for a second if I go back to red-black tree. Yeah, you know, so imagine, just as an example, vector was probably easier. Computer's really struggling. We'll take a break soon. Yeah, so imagine this, right? What happens if like 1 gets deleted, right? Well, 6 is probably going to move itself up. Okay, well, imagine you're a map iterator out there. You're an object, you're a nice little box, and you have a little pointer in you that's just like randomly pointing to one of the objects in the STL container. And right now someone's incremented you and you're pointing at 6. It's a physical memory address because you are pointing to a physical memory address. And then separately over here, you know, this person goes and deletes an element from the map, and the map rebalances itself, and that 6 that was there disappears. So that 6 that I was pointing to, that memory address that contained the 6, that 6 got sucked up and put somewhere else. So what I had before is no longer valid because the structure has been mutated in a way. And every different structure will have a different way of describing iterator invalidation because vectors will shift. I believe vectors shift elements when they're deleted. Pretty sure. What that means is that it says anything at or after is invalidated. Because obviously anything before hasn't been shifted, and therefore it's like fine. But it is something you have to think about a little bit. Now, one reason why this is interesting too is because you'll notice a lot of these functions that invalidate iterators return a new iterator. And this new iterator is really important because here's a really good example of a basic mistake when it comes to this kind of iteration, is that you might have something like, maybe I'll go and change this for a second to, you know, a vector of numbers, and then you go and say, yeah, I got all these numbers up to 7 and 8, and then I say, you know what, can you go and like delete all the numbers that are even? So you say, well, okay, for auto const, what is it? Auto iter equals vec.begin. Iter is not equal vec.end plus iterator. And then you say, well, you know what? If the iterator, if the value of what the iterator is abstractly pointing to is equal to 0, then it's even. So you know what? We'll just go and like erase it. That'll turn out well for us, won't it? Now that you think about it. All right, well, let's go print it out. See what happens. Should have done that, like, pause the video now. Ah! Our worst enemy. It's a horrifying result. Ugh. Segmentation faults. Yeah, so you can imagine what's gone and happened there is like you've got your like imagine you've got 1, 2, 3, 4, 5, 6, 7, 8, and then you start off your iterator points here. It's not even, so you move it up, points there now, and then you're like, yep, it's even. So I actually don't know what's gone wrong here. So you delete it, okay, and then the vector shifts everything forward, but then you increment it after, and then that one's even, so you think I'll delete it, and then I'll shift everything forward, then you increment it. I guess this is what's happening. Yeah, and then you're there. Good point. Let's move this into here. Print statements. Silly person's best friend. That's not what I wanted. Sorry. Should have probably just done that anyway. See, there's tutors. Have anyone got a tutor that's like, here's how you install the debugger? Has anyone done that? I can't do debuggers. They're too hard for me. This is my way of dealing with problems in life. Hey, I wasn't far off. Yeah, so you can probably imagine that at some point then, what's happening is you've got something like this, and let's imagine it's a 6 for a second. And you've got your iterator, it's pointing to the 6. So you come in the loop, yep, you've entered the loop. Is it divisible by 2? Yes. So you erase it, everything shifts down, and then you come back up the top of the loop. It has to increment the iterator. Is that divisible by 2? Yes, great. And then it increments the iterator again, or something like that. I'm not too sure why it's seg faults.
Well, where's it pointing to afterwards?
Yeah, it's going to be something to do with where it's pointing to, for sure. It's just like, it's not, yeah, yep. Yeah, I mean, exactly. Vector end is an iterator, and it would be in, oh, I guess it's computed every time. Yeah, it's probably computed every time through the loop. Yeah, I don't know actually, because this is where the whole compiler thing gets really tricky, because some compilers will cache certain values if they know they're going to be the same. You know, like, there's no point calling a function if the result is constant forever. I imagine that. Yeah, I don't know. It probably doesn't. It probably does call it every time.
But the segmentation fault probably means it doesn't, right?
The segmentation fault's probably going to be because we did this, most likely. Like if you see a segmentation fault in code, you look for the star, you know, because if you don't have the star, like nothing can really go that wrong. Or it's something to do with the erasing of where that's pointing to. But because this is an abstraction, I imagine it handles it better.
So in this case, if you did less than or equal to, or greater than or whatever.
Here,
Yeah, I guess, because the iterator would,
I don't think that will work, but let's try it out.
well, not less than that. You want it to
Yeah, okay. Expected oopsie daisy. What the hell? There you go.
Because in the last one, it just goes, okay, it's passed.
Yeah, so that's really interesting that you think like that, because you're like, well, clearly what's happening here is that because we're shifting things as we delete them, when we increment it, it's kind of jumping too far, you know, to some other point, and then it's dereferencing it. So instead of trying to catch it at that endpoint, what if it accidentally skips the endpoint? We'll just put a less than or equal to, which will handle it, right? Yeah, and
It's a vector as well, right? So we just, but it's an iterator. So
yeah, so like that makes sense as logic, because like what was happening here was, and you kind of followed when hopefully you followed when I was showing you, was like every time we deleted an item, so we moved up one, we deleted it, the whole thing was shifting left, and we were jumping one at the same time. So just to be clear, this just turned out really lucky because I had a whole bunch of even numbers equally spaced. But if we spread this around a little bit and like really messed it up like that, you would also get a very weird result where it would miss numbers too, probably, if my conceptual understanding is correct. We will see. Yeah, see, it missed even numbers in that case because it's shifting and jumping. So it's basically doing like a double step relative to each other, and therefore it's jumping past the end, which is the problem. So this solves it. But again, back to the earliest question about the less than, I haven't tried it, but I imagine this works just because of how the vector iterator happens to be implemented. So this is kind of like a fix that, I mean, not a fix because you shouldn't create the problem in the first place, but this works in this case probably just because of the contiguous memory. And if you did this with a map, it would probably, you know, crap a bunch of bricks. So thank you for adding that because it helps us understand more.
So the end is also moving along with the...
The idea of what the end is, yeah, because I mean, if I put the E there, if I put the E there like that, and then we imagine this for a second, so that it's like, yep, it's not even, move up one, it is even, delete, move, oh, I didn't put the end there. It is even. Great. Delete it. Move up one. Not even. 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 Move up one. It is even. Delete. Move up one. Now we're pointing to the ether, not the end of the array. That's where the seg fault would be coming from. I couldn't look at the code and tell you exactly why. It's not strictly evident to me, but I know that would be the cause of the problem. Which, again, so iterator invalidation of the rules, and it's always in the docs, and they're fairly intuitive, honestly, that tell you when you should consider an iterator garbage and when you need to kind of recollect it again. Oh yeah, sorry, the whole reason I went to this example is because what I'm pretty sure you can do in these cases, and why it's built into the vector and stuff, is every function that, well, not every function, a bunch of functions that invalidate iterators will generally return an iterator themselves. That is like the refreshed iterator. So here you can say iterator equals that. So you're like collecting a fresh iterator that allows you to do these kinds of loops, because these loops are nice, right? Like they're handy loops. So I think, nope, maybe not. What have I done? Semicolon. Thank you so much. Yeah. So that didn't behave like we wanted it to. It dot, say that again.
It's dot advance on the new iterator rather than
Up here. That's interesting. It's still skipping one.
Yes, if you only added outside that if statement, what would happen there? I guess that would work because it's shifted backwards and now it's pointing at the next line. So plus it should just be like outside that if statement of the modules.
There is no plus plus it in the if statement.
Not the if statement, the for statement, but just keep it, because it would do that regardless, right?
Yep.
Oh, okay.
Oh, do you mean like this or something?
Yeah,
No, it doesn't work. No, it's That's interesting. This is what I get for trying to write some code on the fly, but yeah.
We have the plus it. When you reassign it, say it equals vector arrays, we have to subtract, like do it minus it, so the next time it adds to it.
Maybe. I'll try that. That should be, so the return value is the iterator following the last element removed. Yeah, so that makes sense, and that's kind of what you were saying too. I'm not sure why the else didn't work though.
probably less than or equal to.
Oh yeah, Jesus. Let's hide that away. Yeah, so we can try that out, see if this one works this time. Leave me alone.
I don't think this
Oh,
matters.
cool. Awesome. See, I love that, isn't it? It's a little bit, I didn't pick up on that clearly. But I love that. And you know what? I think it's important about things like this, because I'm often just like bashing away at code real quick. If you weren't sure, right? Like many of you right there probably would have been like me and been like, what the hell? You just go read the docs and reason with it. It returns an iterator following the last element removed. And then all you have to do is do your stupid little list, 1, 2, 4, 5, 5, 7, 7, 8, and just reason with it. So think, well, iterator's pointing to 1. I increment it.
So why return the iterator? Because you can do this otherwise as well, right? This is working even if you return or don't return. If I just do wait dot erase it, I think it will still work the same way.
You're saying that we don't really need that part. I get what you're saying. I don't have a confident answer here. I get what you're saying. It's intuitive. I think off the top of my head, I would imagine that the only problem with that is that without the abstraction, you're probably maybe relying on some assumptions about how it's structured potentially. It's probably different for different containers too. This works for a vector again. It's probably like the less than or equal to. It's just I wouldn't rely on that thinking for every single container. But play around with it, right? That's the fun part. It's just playing around with it. Yeah, Tim on the YouTube chat says that for loop is about as close to a while loop as a for loop can be. Yeah, that's very true. Very messy though. I often talk about like, we talk about like don't use ChatGPT and LLMs when you're learning. I use ChatGPT a lot, particularly for shell command stuff. I was trying to do all these I have these like big files from like travel I did last year, really big video files, and I've been trying to like compress them down, and ChatGPT has been like a wonder, just being like, please help me compress my video files. What do I type into the terminal? But a good example here is if you just said to ChatGPT, and I'm not going to do it because I don't want to encourage you too much because you'll get out of hand. It's like, I want to move through a C++ vector of ints and remove all even numbers via the method erase using iterators and being careful of iterator invalidation. Please help me. You'll get a good answer. I find what I find funny about ChatGPT, a little bit of a tangent just because we're kind of at the end of this one. I feel like what happened was, we all have to learn English in school, and then the age of Google and stuff kind of taught us to be very un-Englishy, like what you type into Google is very like robotic, like best syrup Sydney, yes. And because ChatGPT is trained on like English language, I think it's kind of funny that we'll have to get better at expressing ourselves again. Because if anyone's used these LLMs, it's like you nearly have to tap back into that more descriptive human part of your brain, because everything it's trained on is human in nature. It's like people talking. So I love honestly, don't treat it like Google either. Talk to it. Like it understands you and your feelings. Yeah.
I think vector is known for the way vector is constructed, that you can access all elements individually, right? So I can.
Yep.
So for erasing one of the elements, why do we have to go through erase? Why there isn't a function or a method that I can erase one particular element directly? Why do I have to kind of go as a list and go to that particular item and then delete?
I think there is.
I don't understand the question. You mean like why do you have to iterate through it?
Why is there a method?
Yeah, is there a method to directly erase one particular element?
So just the normal like Python way to scroll.
Well, I think there was something like indices, maybe.
Like a find.
Or index.
No, just like dot remove. Like for I, if I was set to.
Oh, I don't know.
I think there is. Probably is.
Maybe. I'm flattered that you all think I know everything sometimes. Like I have no idea. If I had to guess, I mean, if there isn't a method, and I don't think I saw one, like it's erase, pop back. I don't know, but I just have to guess, and I'm just speculating. It's probably because like if you were to just reference particular indexes and delete them, maybe that would break an abstraction. I don't know. I can't really see why they wouldn't just have like a delete and then you give it an index. The fact that it doesn't exist would imply that there's a reason for it. It's a very common, powerful library. So I can't see why they just be like, oh, we just never got around to it. It's there's probably some smart-ass reason that I don't understand.
Is the iterator actually reducing memory here as well?
Is the iterator reducing memory?
Yeah, so when you erase stuff, is that when you've got like, let's say your memory was pushed up, double whatever sizes, then you let it out.
Oh yeah, so if we're just talking about the memory of the container, I don't know. Again, I have to go read the docs. But just from what I have read, unless someone else knows, from what I've read, it'll double its size every time it has to expand. But I don't think it shrinks. Again, C++ being a much more unmanaged language than other things, that's probably why there's a resize function as well. Maybe there is one, but a lot, you'll see this theme a lot, right? Like in the spirit of being unmanaged, because like, what if you're constantly expanding and contracting a list? You don't want to be carrying the overhead of all those you know, malloc calls and free calls and things, potentially. But again, I don't know. I don't think it says anything about size or capacity. You'd look for those keywords, right? Because that's how it's described. But it's interesting. Shrink to fit. Yeah, here you go. So if you think about reading these docs, what you would do is if you knew you had a big fat 1,000 item vector and you deleted most of them, you'd probably say vector.resize vector.size, probably something like that. You know, that makes sense. And then someone's come along here and added a shrink to fit, which would just be the same thing but a bit clearer. Daniel has just on the chat asked me to bump it, then we'll wrap up this one. He said, how does a star operator implementation avoid returning just a copy of the value? It probably returns a reference. I understand that question. It's probably a bit heady to unpack at this point, but it probably just, because you can have functions return references. We covered this again in week 5, but like in week 5 we'll bring this up, but there's an interesting thought, which is imagine you have a main function, and that main function says, yep, int a equals high. And then you've got a function here called high, and it does this. Now, if you think about that program for a second, it's a little problematic, because you're declaring this variable b on the stack, and then you're returning b, which is fine. You can declare things and return them. However, if you look at the return type itself is an integer reference. So it's saying you don't want to go and copy all the contents of b into the stack to return it. You actually just want to give a reference to it. So whoever's asking for it gets a reference to that memory. But the problem is b goes out of scope when the function ends. Because like when you create functions, you know, you create a function, stack frame, all that crap, and then gets created. B is gone. So now suddenly you've got this like reference to something that doesn't exist anymore in memory. This kind of works okay though with a heap element. For instance, if you kind of had like more of a, you know, an instar. I don't even know how you do instar reference, if that even makes sense. Doesn't even make sense. You kind of have a reference to a pointer because it's the same size. Anyway, whatever. This works with malloc because you know, this unmanaged, can't remember the name of it. Malloc stuff lasts forever till you free it. So it's fine to have a function create something. The function vanishes forever, but there's like the reference to that memory carries on for a long time. But anyway, the question was like, how does operator avoid returning just a copy of it? I imagine that because it's malloc the memory, it can return a reference to the thing it's pointing to. That doesn't make sense. I wouldn't really care because I might have explained it weird, and then regardless, it doesn't even matter. But let's take a short break for 5 minutes, and then we'll keep going.